This lecture is about backpropagation. So this is really an effort to give everyone a high-level understanding of how auto-differentiation software actually works. This is meant to make anyone here an expert at this type of software, right? But if you gain interest through this in introductory material, it's a starting point to learn more, really. So how does TensorFlow actually under the hood enable you to solve these machine learning problems efficiently? And why is that unique compared to other software, right? Why is everyone using TensorFlow and PyTorch, basically? Why is that like a new thing? Why can't you just do deep learning optimization using existing software? Hopefully this lecture gives you an inkling of why they're unique software packages and lets you, also jointly appreciate how the uniqueness of that software works might impact the way you need to code, and also some of the limitations you might be encountering when you are coding and you get a little frustrated and say, hey, why can't I do this standard coding procedure that I'm used to, for example, in NumPy or MATLAB? Why is TensorFlow not allowing me to do this? This hopefully lets you understand why. Okay, before I get started, are there any questions or concerns about things organizationally? Are we all? Yeah. So next class, we'll talk more about the final project again, and I'm trying to think what else. And then this lecture we're very numerical, which is boring to some people. So hopefully, I told Ramana to get some cookies for everyone to keep everyone awake, which I've noticed helps. So hopefully he shows up with those. Fingers crossed. I don't know where he is, but hope he's okay. I think he'll hopefully come with cookies. This is our pipeline, right? So I won't dwell on this. It's just to get everyone recentered thinking about this class. We know a lot of these boxes, right? I hope, and how to implement them slowly in software. Hope that's becoming clear. The key missing point isn't setting up these boxes. I feel like we're all comfortable, hopefully, with that a bit. It's when you press enter on TensorFlow and how the minimization of your loss function L actually leads to weights working their way into numbers that make your machine learning code actually work, right? In other words, how does TensorFlow change the weights in these general weight matrices to make this loss low, which means that the network is actually predicting what the correct label for each of your images is for all of your training examples. Okay, so I'll quickly go over this introductory material. And so here's a review of gradient descent, right? We already covered gradient descent. In short, we have a function and we want to find the minimum of the function. And so there's multiple approaches to doing that, but naturally one that is computationally tractable is to rely on computing gradients. Because if you know the gradient of the function, you can always go down the function, so to speak, down the hill. Head in the direction that correctly makes you go towards the area where the function, when it's minimized, is smaller and smaller. Okay? And computers are great at that, naturally, that's why we talk about it so much. But to do that, you just set up a loop and you update the weights to make the function of interest smaller, right? And so to do that, you evaluate the gradient. That's the key thing we're going to talk about today. And then you subtract that gradient from the variables that you're minimizing iteratively. And how much you subtract from the variables is up to you. And it's called the step size, right? If you change those variables too much, you may overshoot the minimum and end up somewhere else that's back up high values, right? And if you go too little, you're taking too small of a step and you won't necessarily make progress computationally efficiently towards the goal of minimizing the function L. But what's really important is this evaluate gradient step. All of those complexities aside, let's just assume you can figure them out, right? Or people have figured them out before. What's really tricky is this evaluate gradient function in the context of deep neural networks. For shallower, simpler problems, shallower meaning like a simpler function for L, we've already seen 3 possible options for this evaluate gradient function. One is we can evaluate it numerically. The other is analytically, and a third is what we'll talk about today, which is effectively a joint combination of numerical and analytical. So this pseudocode, I'll note, is a form of steepest descent, effectively, right? We're changing the weights, you'll see in both of these. This one is steepest descent in the sense that it's directly just subtracting the gradient from the current values. You don't have to do that. And TensorFlow won't do that for pretty much all of the methodologies you'll select, but it'll compute some function of the gradient, right? It'll rely on the gradient in some capacity, right? So I just want to make that clear. You still need to evaluate the gradient. This is a numerical evaluation, right? We went over this. You can do this in a brute force way, right? Which we tried or thought about. And the gradient is the extension of this derivative in the red box to just a vector, right? More than one dimension. You're doing it across multiple variables. And you just compute each of those three terms. One of the terms, h, you set it, and then you compute the other two. And so if we have some weights at a current iteration, and then we compute the loss with those weights, right? Just with some example images and their labels. And then we say, oh, that looks high, right? Or maybe not, but let's just try to make it lower. So let's perturb one of the weights. We'll pick one of them and add a tiny bit to it, 0.001. And then we'll try those new weights out. And you'll see if the loss goes up or down. Just establish that, and if it goes up, that's bad. You change the weights in the wrong direction, and if it goes down, that's great. You picked a good direction to alter the weights in. And so you should continue to do that, right? And so the aggregate of that across all of the weights is your derivative. It's very slow to do this, right? It's not a good idea, but it's just an option that connects to the operation of TensorFlow, as we'll see. The other option is to do an analytical kind of calculation, or to write out the gradient analytically and then implement that in your code. So we did that on the homework, right? We figured out, oh, it's a linear classifier. We can work through that math and come up with the idea that to minimize the mean squared error loss function, we can rely on the pseudo inverse, right? So that's also what TensorFlow is going to do. It's going to do both of these things, but we haven't looked at that intersection. We just considered that as a single example. Okay, so automatic differentiation effectively sits at the nexus of those two ideas. Just the resources I used to put this lecture together. Most of what I talk about is contained within the Stanford CS231N lecture notes, which I'll actually use. I just want to really cite that because I think that class did a wonderful job at putting this material together, but I also relied on these other two references to help with this. And yeah, I'll also preface this by saying I'm not an expert at automatic differentiation. I don't think there are many in academia because you get paid so much to work at companies who need to develop this software. But I just have read about it and know enough about it to be dangerous. But it's really, this lecture again is more of a high-level introduction. It's to make sure you guys at least understand a little bit of what's going on under the hood, not to be experts. So, what is automatic differentiation? It is essentially a way to take a long, complicated set of split them into elementary operations. And it'll then perform multiplications and associated derivative multiplications analytically. So I'll explain that in a second. It fundamentally needs to save what it's doing across all of its steps. So that's really important. When TensorFlow operates, it doesn't just take stuff and then give you your end result, right? It saves things, intermediate things, all along the way. Why? Because it needs to use those in its process of computing and passing on gradients. So it is memory intensive, right? Unlike other coding procedures, more memory intensive. Here's a very simple example that I liked that explains automatic differentiation from a bird's eye perspective. Let's say you have a function, and this function can be defined recursively, right? So this is just a short way to say, here is a numerical problem that has many steps, right? Not all recursive functions should be evaluated with automatic differentiation, nor does the power of automatic differentiation really shine with recursive functions. This is, again, just an illustration. But here's this function where it's very simple, right? It's x is input, and then you evaluate L, where L is equal to the previous value of L times 4 times 1 minus L, right? At the fourth step, you get a pretty long equation already, right? 64x times 1 minus x, blah, blah, blah. I won't read it all out, but long enough that if you were in high school and you saw that on a derivatives exam, you would not be happy, right? You would already have to mentally reserve like a piece of paper to start doing all of these calculations. And so manually differentiating that is annoying, right? It's annoying for L of 4, but imagine L of 40. It's impractical, right? It's not something anyone would ever do. And so you can go ahead and do that on a piece of paper and then handwrite the derivative out in code, which is what I had to do in grad school to get optimization code work, specifically for non-convex problems. You had to assign the gradient. There wasn't any. There were auto-differentiation software packages. They were not in the mainstream yet. I didn't know about them. Anyways, that was the status quo. Everyone was doing this. And you'd make an error. This would be like a plus by accident, and then nothing would work, right? And you'd pull your hair out and be kind of in the weeds trying to get everything to work. So it was not conducive to rapid progress. You would naturally not necessarily try that approach if you wrote out your recursive function in code, right? It would automatically reveal itself that this recursive relationship could potentially be exploited to help you compute this gradient. So if you write this out in code, either in recursive form or in closed form, you could imagine, specifically in closed form, if you wrote this equation out, you could imagine going to Wolfram alpha type approach, and then software can do a symbolic differentiation of this code, right? So there is a way to get this derivative, but that's not the most efficient way you can compute it. And then we saw numerical differentiation. This is what we just resorted to on 2 slides ago, right? You say, hey, I have this really complicated function. I'm just going to add a little bit to it, see how the values were perturbed, compute numerically the difference, and try to establish a gradient that way. Also, as we've seen, very slow. Okay, automatic differentiation is this insight that if you have a complicated function that you can split up into elementary operations, which for this recursive function is trivial, you can, as shown here, write out the function, just like we did here, and then you just keep multiplying it as you recur along to evaluate the function, right? You can also, by hand, compute its derivative, but only at the single point where you're considering the nth iteration. So at the nth iteration, the value of the function is 4 L of n times 1 minus L of n, right? The derivative of that function at that iteration is 4 times the derivative of L of n minus 8 times L of n times the derivative of L of n, right? And that's just simply by passing that through, right? 4 L of n minus 4 L of n squared. You take the derivative of each of those, and you get this result, okay? And so using the chain rule, that derivative is just going to pass on each time through a multiplication as well. And so you have done 2 things. You've gone ahead and did a manual kind of by hand derivative. You had to compute that derivative of the recursive function, but just of a simple function. And then we're numerically going to pass it along, multiplying it iteration by iteration. Okay, so that's what automatic differentiation does at a high level. And it leads to very compact code. This bottom left box is just an additional couple lines where you have to evaluate the derivative, but then there's a good amount of machinery behind that that you need to create, or TensorFlow has created, to be able to pass that on, right? Each derivative needs to be applied somewhere, right? And cast across the web of all the calculations you're computing. So that's, yeah, what we'll talk about in a second. All right, are there any questions about that kind of very high level introduction to this bottom left box, automatic differentiation? Kind of makes sense? A little bit? Okay, I think it'll become more clear. And so how does this extend to more complicated equations, right? We're not just doing recursive equations, we're multiplying all these weight matrices and images and stuff like that. And for an arbitrary set of computations, you can create a connected graph. I hope that concept is clear. You've seen these before, where you can take operations and split them up. And you say, numbers come in here, we're going to add them, that's at one node, we're going to multiply them, that's at another node, we're going to divide them, whatever the case may be. This is done computationally all the time, right? So if that isn't clear, I hope you take my word for it. That is an important concept you should read about if you're interested in computational modeling or numerical software at all, right? So here's a very simple equation, again, for illustrative purposes, that evaluates two scalar values, x1 and x2. And just arbitrarily, it's going to compute the natural log, or the first, multiply them, add that, and then subtract the sign. You can create this computational graph that shows that entire process. Okay? So that's straightforward and is done a lot. It can become much more complicated than this, but every computation has at least one computational graph that you can create for it. So it's not a unique computational graph. There can be multiple graphs for a particular problem, but this is always possible to do. We are going to use these graphs, or TensorFlow rather uses these graphs to perform all of its gradients as well. And so it's worth going through this as an example. And what we need to do at each node in the graph is not just know what computation we're performing, like sine of, or natural log of, or addition. We also need to know the associated derivative or gradient of that operation. Right? TensorFlow knows that. It's hard-coded into TensorFlow. I'll get to that in a second. But in TensorFlow, or in any auto-differentiation software, there's computations that flow forward, so that's from left to right, and then backwards, right to left. And so you always start going forwards, right? And so we can go ahead and just evaluate this function for some input values x1 and x2. You cannot start doing the backwards evaluation to figure out the gradients until you've gone forward once, right? So fundamentally, we always have to go forward first. So to go forward, we have some values x1 and x2. Here it's 2 and 5. We can compute the intermediate values v-1, v0, v1, v2, etc. that populate this list. Each of those is just like pushing a button on a calculator, right? TensorFlow is going to save all of these values, right? So all of these intermediate nodes you need to save. You can't just do them. You have to put them in memory, okay? That's important. Hence the memory-intensive nature of auto-differentiation software. And naturally, this function, right, is extremely simple. TensorFlow, you have millions of weights, millions of operations, billions of operations sometimes. And so this is gigabytes at times, right? It's a big ask for larger models. Okay, so this is an intermediate step where we're going to talk about a way to evaluate derivatives, okay, through this graph. And what we can do is, once we have this forward evaluation table, or this is called a forward trace, we're now going to try to use that to efficiently evaluate the derivatives of x1 and x2. All right, so to do that, we can say, all right, I'm interested in the derivative of x1. So dx dy1 equals 1. And then all the other inputs I'm going to set to 0. And so the way I think about this, and I'm pretty sure it's a good mental picture to have for these networks because I haven't encountered any issues with it so far, is I think of these vectors here of inputs and weights and outputs as being numbers that you can wiggle. You're perturbing the inputs or perturbing the network or perturbing the output. And so what you can do is, if you're interested in derivatives, you set everything to 0 and you wiggle one of the values by setting it to 1, let's say. And you then see how that cascades to the network, right? And so here we're going to wiggle x1 and x2 will be 0. And we then have at each node, like I said, TensorFlow is going to save the derivative of each operation. And so at v1, which is the natural log, the derivative of the natural log is 1 over the value of the natural log, right? And so we have this derivative value saved here, right? So for 1, that's going to equal 1/2. 1 coming in, we'll get 1/2 at the output there. V2 is a multiplication operation. So a multiply, right, is A times B. And so you use the chain rule. The derivative that TensorFlow is going to save is A times the derivative of B plus B times the derivative of A, which is written out right here. A and B are also nodes in the network, right? That's important. So have this coming in from our definition of x1 up here is 1. And V0 is the A times derivative of B. It's the actual value from before, right? And so that's why this forward table is really important. We're going to go find V0 over here. It was 5, right? Then we'll do the same for V0 derivative, comes from our definition in this table, but V-1 also is from the first table over there that we saved. And so you can see how all of these equations that evaluate, that use the derivative as it's going through the network are going to rely on values that were created in our formal trace at each node. Right, so the next one is the sine V3. Here it becomes a cosine. But it's cosine times the value within the thing itself because of the chain rule, right? And so we need to go back, find V0. It was 5, plug it into cosine, multiply it by the derivative V0 dot, which from our definition we said was 0, etc. So the add becomes similarly an add, subtract a subtract, but of the respective derivatives. And right, we just plug all those numerical values in and we get 5.5. So all of those derivatives we computed are local derivatives, right? They're just the derivative of the node itself, right? The natural log, we just consider that and create its derivative. Okay, so this is not how TensorFlow works. It's evaluating the derivatives going forward still, which is slow. Why is it slow? Because we had to compute all of those values, node by node, just for the derivative of x1. And then we're going to have to repeat all of those computations for x2 and x3, x4, x5. All those x's, by the way, are your weights, w, because each one we need to evaluate the gradient of. And so if you have a network with 100,000 weights, that's 100,000 forward passes just to get one gradient. So every iteration, you're doing hundreds of thousands of complete evaluations of your network, right, which is very slow. Okay, and so the way TensorFlow actually works is it takes that wiggling. So here we're wiggling each input derivative and seeing how that cascades to the output. We're going to work backwards. And so what we're going to do is wiggle the derivative of f over here and see how that cascades through the network to influence all of our input derivatives. That's called backpropagation. And I'll explain that next. And really what backpropagation does is, instead of looking at how the gradients flow going this way, which is what we talked about, now we're going to start wiggling and seeing how things go backwards. And so to do that, we need to use the chain rule. Not surprisingly, it's the same chain rule that was allowing us to go forward, but we're just going to reverse the operation a little bit. We're going to take the loss and compute its gradient locally with respect to the values right here, and then pass that through each node of our network. We're going to say, hey, here's a little wiggle. Split that little wiggle in terms of how it's influencing things further downstream using the local chain rule, right? Just using the little operation that you just computed, send those gradients along their way in the right proportions to the next nodes and the next nodes and the next nodes, right? And so if this was f equals x times y, each of those is equally important in its gradient as well, then you would just split up the gradient here into the x and y, respectively. If it's x plus y, similarly important. If it's x squared times y, then you need to do something a little bit more complicated, right? Does that kind of make sense? So it's, to me, this little process of passing messages backwards through the network, saying, hey, here's the gradient. Look at the computation. You just take that gradient, pass it along as important as it should be to each of the variables that just came in to compute that, right? And that just continues and continues. All right, and so to understand that, we're going to go over some very simple slides that I think illustrate the concept well. And they're from this Stanford lecture that I mentioned. And I think I tried to come up with a better set of slides, but I didn't. They were worse. I think so. I'm sticking with these. Okay, so here's a very simple computational graph again. And here we're going to do back propagation, not the forward evaluation of the gradient. So we have three inputs, x, y, z, and the equation, the loss function, quote unquote, is x plus y times z. Right, so very simple. And then our inputs right now are -2, 5, and -4. So we have to go forward first. So first we evaluate f. Very simple. -2 plus 5 equals 3, and then z is multiplied by that. So remember, we have to save all those intermediate values though. So there is an intermediate value here we need to save. And we can go ahead and look at the gradients locally, right? This is pretty simple. So if we have q equals x plus y, q is the definition of this intermediate node, then we get two gradients, dq dx, dq dy, both of those are 1, right? That's simple enough because we're starting with a very simple example. And then the intermediate value, or the final value actually here, is q times z, right? And so the derivative of f with respect to q, we always evaluate it with whatever arrow is coming in. We're not going to consider df dx, that's one far removed. There's no local connections there. So df dq and df dz we can write out as well. They're just equal to the respective value of each, right? The other value, right? So df dq equals z, df dz equals q, okay? Let's go backwards. We're going to say how should we wiggle the network? We just take df df. So essentially in the gradient space, we're going to be writing red numbers here. We're going to input a 1. Just like we input a 1 before, going forward for the value of x1, the first weight we were interested in. Now we're going to just input a 1 at the end of the network. You always have a scalar loss function. You have a single value at the output. So you just send in 1 in this like gradient space, I'll call it in quotes. So that's the gradient. How does the gradient influence our first value z? We computed it directly. df dz equals q, right? And q we had right here. We numerically evaluated it and saved it. It's 3. So we can go ahead and pass 3 to the gradient of our variable z, right? That one's really simple because z connects all the way to f directly. You'll never have any weights, very rarely any weights that connect all the way to your loss function, unless you put some weights directly into your loss function, which never seen happen. That's a really easy one. It won't be that easy. So now we need to go to x and y. We have to work through this part of the network, right? All right, so to do that, we first have to go through q, right? So we have to say, how does our wiggle of the loss in gradient space 1 go influence q? And so we need to evaluate df dq, right? That isn't anything related to our weights. Q has nothing to do with x, y, and z, which are our weights of interest, but we still need to evaluate it to figure out the gradients that we want, right? And so this again, like TensorFlow, has to save all the forward values and also all of these local gradients of things you're not really interested in. Q we just made up. It's not part of our original problem. We're not trying to optimize Q, but we need to save it to then get to what we want, okay? So what's df dq? Luckily, we wrote it down here. It's z. We computed it. It's just from the multiplication operation. And so z we have. Z is -4, right? It's in the green text up there. It's one of our inputs, one of our green values, okay? So we have -4, and now we need to pass that through the plus operation. So what's df dy? This is where the chain rule comes in. df dy is the product of the gradient coming in here, which is this red value, it's df dq, times dq dy, which is a gradient that's in this bubble. TensorFlow is going to save it. We computed it by hand over here. dq dy is 1, but it's just going to be saved in this node, just like this node saved these df dz, df dq, right? And so we need to take the red value here that we just figured out and multiply it by something that we have associated with the add operation that TensorFlow is going to save. And so that's 1 in this case, just because it's really easy. But it doesn't have to be 1. It could be something else if that wasn't just an addition operation, okay? And then the last one, df dx. Right? Same, we're going to use the chain rule, df dq, the red value, -4, times dq dx. Again, 1, we get -4. All right, we did it. We did our first back propagation. Everyone give yourself a hand. Now you guys can say you're experts at back propagation. So like I said, you get a wiggle here, this gradient coming in, and then you have this local gradient information saved for the particular computation you're doing, and you just pass the incoming wiggle along accordingly, right? That's what the job of TensorFlow is. And so you get dl dx, the derivative of the output of interest with respect to that variable that you're then going to continue to consider by multiplying dl dz, which is what's coming into the node, times dz dx, which is this internal gradient information that's just exclusive to this local operation, a sine or a natural log or a squaring or whatever, okay? And then same with y. And then those go to new nodes over there, and it keeps going, right? Step by step. Okay, so let's do this slightly more relevant example. Here we have we've seen this equation before, 1 over 1 plus e to the negative a. You guys remember what that is? The sigmoid, yeah, I saw someone draw it. Sigmoid, or people call it the softmax too, okay? So it's a softmax of w0, x0 plus w1, x1 plus w2, which is like a linear classifier, right? So this isn't really a real loss function, but it's getting closer to the types of loss function you'll see, because you have at the penultimate layer of some logistic classifier, this sigmoid evaluated of this linear boundary someone might be trying to draw, right? Okay, so a somewhat more realistic example, still incredibly simple, but you can see how complex the graph already is. It is hard to read, right? But we can walk through it still. So we have multiple operations that are each split up into this in this computational graph. How simple of an operation does TensorFlow split these up? Not this simple. It doesn't go, it has like a whole function that is just sigmoid and then the derivative of a sigmoid, right? But here we've split up the sigmoid into 5 individual nodes, but that's just more for illustrative purposes, right? Okay, and so we have, again, a forward pass of this. We need to have inputs, and not just weights, but also x's. So we're fully evaluating everything in a forward pass. And so here, x1, x2, I'm not going to say their numbers, but you can read them, and some weights. We go ahead and do these multiplications of the different x's and w's, add them, 1 plus, and then get to this 1 over thing, okay? So each of those has a value. Now we're going to do the same thing. We're going to go into gradient space. The green numbers are our forward pass. Red numbers are our gradient space, backwards propagation. So we start with a 1 here. And then we see, hey, how do we pass this through this node, right? And so the derivative of 1 over x equals -1 over x squared. And so we need to use that local information. And so what we're going to do is take this 1 and multiply it by 1 over x squared, x being the input into this network. So -1 over 1.37 squared equals -0.53, right? So that's going to be our gradient coming out of that node, right? And we're going to pass that along. So now we need to pass 0.53 into the next node, which is a +1 operator. The gradient of +1 is 1, right? X plus a constant, you just get a constant. So we have, it's this pattern, right? By going through this example, I'm trying to show this pattern. So we're now at the next step. We have 0.53 there, and we want to pass it through this x plus constant type operation. The derivative of that is 1. So it's really easy. It's like a lookup table. For a lot of these computations, you just pass the gradient directly, right? There's no computations needed. So then we're at this exponential. The derivative of an exponential is an exponential. So we're going to take 0.53, multiply that by the exponential raised to the -1, right? And then that's our output. That's our new red value. So e to the -1 times -0.53, right? We get -0.2. Same there. We're going to take -0.2, multiply it by -1, right? Because the derivative of this is a -1 operator, and we get 0.2. So when you have a negative sign in TensorFlow, immediately in gradient world, you flip the gradient as well, right? That's just how the chain rule works, right, in this process. So now we're at a node, right? We have two things coming in to this plus operator. Plus, remember, in gradient world, that means you equally send the gradient along the two directions, because when you add two things, the gradient is equally important for those two things, right, coming out. So we're going to take 0.2 and just pass it along to both directions. This one gets a 0.2 and this one gets a 0.2, right? In other words, when you wiggle the gradient on the right-hand side for an addition operator, that means send it along both equally as important. Okay, and then we can keep going. So we already got W2 though. See, we got the gradient of W2 already. So we're 1/5 of the way, 1/3 of the way done, because we only had 3 weights of interest. We don't care about the derivatives of x1 and x2. Okay, and so then we have a 0.2, again a plus, we pass it along, and then a multiply operator. We've already done this one. You just multiply 0.2 by the other value that came in. So the 0.2 to get to the weight W0, we'll multiply it by x0. And that's 0.2 times -1 equals -0.2. And then the opposite for x0, we'll take 0.2, the incoming gradient, and multiply it by W0 to get the gradient for x0. And so that's 0.2 times 2, and that's 0.4. Okay? So there we've done our gradient descent on our almost realistic logistic classifier type problem for a single iteration, for a single input x. So repeat that for 60,000 inputs x, where for each of those you probably need to do 1,000 iterations to get to the bottom of the hill. And that's what TensorFlow does. You remember from math a long time ago, those you say, oh, the gradient can't be defined or whatever. And so typically TensorFlow neglects those and evaluate those. It doesn't treat the problem from a holistic mathematical perspective. It effectively skips it or makes an approximation, right? And in aggregate, that approach works because you have millions and millions of these operations cascading, and never does TensorFlow guarantee you'll reach some global minimum or anything. It's essentially just trying to get to an effective local minimum. So we talked about what happens when in these graphs where the gradients have to go into a node, one gradient comes in, and then it gets split up, and it kept splitting and splitting. But we didn't ever really encounter where there were 2 red values coming into one node, just in those simple examples. But that does happen, and when that happens, the gradients just add. I think that's a natural question. Values, if they're both coming in to a particular computational node, you have multiple gradients coming in, you just add them up before multiplying them via the chain rule. So that's an extra aside that I didn't want to skip. Okay, and this is what the code looks like, again, in pseudocode format, right? We have this forward and backwards operator that every person who's writing TensorFlow code needs to just do. It probably was really time-consuming, and is why updates, including new functionalities, are slower in TensorFlow. For example, I don't think complex values were supported in TensorFlow until 2021. Even though at least I started using it in 2015 or 2016, and there were many requests for adding in complex values. And the reason why is because then, if they wanted to accommodate that, they had to rewrite not just all the forward operators to be consistent with complex numbers, but also all the derivatives. And maybe they just didn't have enough people that knew derivatives of complex functions, or they just thought there were bigger fish to fry, probably the latter, but it just took that long, right? So that's a complexity of auto-differentiation software that you don't see, but just exists. Every operator has this backwards pass evaluation code baked in. Okay, and that's why it can be so efficient. And so that's this aspect of auto-differentiation that I spoke to, where it's somewhat analytical, and somewhat numerical. The analytical derivatives are baked into these operators, each mathematical operation. Right? Here, multiply is just shown, but you can imagine every mathematical operation having something similar. Okay, and so how exactly does TensorFlow create a graph structure for backprop? So this is relating to the question we just had. It's complicated. Detail on this, but then TensorFlow changed what they were doing, and so then I decided not to include those details in this lecture too much. But there is a whole guide to these graphs at this link, TensorFlow's guide. If you're really interested in this, go check it out. You can create these visualizations of your own code very easily, right? I don't know, there's just some simple TensorFlow functions. You say, show me the graph or something like that, and it'll just show you the computational graph that is. And then I would imagine if you are trying to optimize for efficiency, we'll show you maybe where it's splitting graph areas off for parallelization. So tf.graph, it's that easy. So if you are really interested in this, go ahead and play with these functions in your code, and it'll show you what it's attempting to do. Okay, and then the last thing, I will quickly go through this because everything I've shown so far has just been with scalar math. TensorFlow has the additional complexity of needing to do all of this with matrix and vector derivatives. And so I'll quickly go through an example of that, which becomes quite complicated for our own analyses, right? Which is one reason I guess I'm showing this is to motivate why backpropagation leads to this conceptual issue of people considering TensorFlow a real black box and hard to interpret in conjunction with people making deep networks with lots of operations. These types of passage of gradients through these computational graphs that can be large becomes what people say is intractable or hard to follow, right? The flip side of this is that, like I've mentioned before, computers are very good and efficient at computing matrix and vector derivatives, right? It's a particular area where humans are, I think, really bad at efficiently understanding what's going on, but computers are particularly good at numerically evaluating. And so it leads to this conflict and issue in machine learning where people say, hey, that's not interpretable, or I don't understand what's going on. Right? And so this is just a reminder of matrix and vector derivatives, right? So just like computing things for a forward pass, we need to shift from scalar operations to matrix vector operations. Now, backwards pass, we need to shift from just chain rule to matrix or vector-based chain rule, which is really not that hard. You just need to be careful about what you're doing, but I'll show you an example. Okay, so now is a slightly more realistic example, and I'll just go through this really quickly. We have this pretty realistic loss function now. We have a two-layer neural network where W1 and W2 are weight matrices. Our inputs are X, and I didn't include the labels here. Y, you would have Y minus this squared or something, or we have the L2, so it is squared already. I just didn't include Y's. And we're interested in what's the gradient of the loss with respect to the matrix W1 and W2, a matrix derivative, right? And so we can get all of these weights in matrix form as well. We don't need to go weight by weight necessarily, which is this nice advantage of shifting our scalar math into vector and matrix math. Okay, and so here's a simple computational graph we can make for this problem. We have 4 intermediate nodes here. So the first one is multiplying X and W. The second one is this ReLU operator. The third one is multiplying W2 and the output of the ReLU. And the last is the absolute value, or the magnitude squared summed up, the Euclidean sum of the values of Y. Okay? And so we need to evaluate in a forward pass each of these red values. We'll save them. Then we'll go backwards. So to go backwards, we'll first, I don't know why, but it's always been easier to start at the bottom weight, and there's less arrows in all 3 of these examples I've gone through. But this one is the same, so we'll start with W2 on the bottom. So the derivative of the loss with respect to the matrix W2 is equal to the derivative of the intermediate value Y with respect to the matrix W2 times the derivative of the loss with respect to Y, right? So we pass the gradient here, multiply it with the local gradient here, and send it along down the way, okay? And we'll start off with evaluating those two vector derivatives or matrix derivatives. The first vector derivative, you get 2y. That one's kind of like scalar math, so we're good. And then the second one is H1 transpose. Why is it H1 transpose? We can work out the dimensionality of it. It's just, it is. And so the output is going to be the product of those two vectors, right? So dl dw2 is equal to, and then there's a factor of 2, sorry. So 2 H1 transpose y hat, right? So that one's pretty easy. Okay, so we got one, and then let's do the next two. Okay, so now we need to go up to this upper computational graph path to get to the derivative of the loss with respect to W1. Then we're done. We've gotten all of our weights updated. We've gotten dl dw2 and dl dw1. We can go ahead and take a step down the hill, so to speak. And so we need to go up through this path, right? And so we're going to pass this gradient through here, and then this gradient up to H1. And we have dl dy coming in here is 2y hat, and dy dh1 is going to equal the W2 matrix. So we'll multiply those two. And so we get 2y hat W transpose, these two multiplied together coming into this node. And so then we need to multiply that with the local derivative of the ReLU operator, which is confusing because it's a vector, but it turns out that that vector, sorry, the derivative of h1 with respect to z, right, dh1 dz, equals an indicator function, right? This is saying pass along the values, because you remember the ReLU operator is this, it's 0 over here. So the gradient also is 0, and then here the gradient is just 1, the value coming in itself. It's the gradient's 1, and so if you're multiplying anything with this gradient, you just pass along the values that are multiplied in this sector of that vector, which is this indicator function I. And we're almost there. So now we've gotten to the last node. The derivative of z with respect to W1 is x. And so the last thing we need to do is multiply the value in this red box with x transpose because of vector math. And so our final expression for the weights W1 is this rather long equation, 2 x transpose y hat W2 transpose times this indicator function. Okay, and so you can see it's all possible. It's just really complicated and annoying, especially to do by hand and evaluate things and where they've gone wrong and things like that, which leads to this big interpretability problem. It's essentially doing the same thing as the scalar case. It's just that extra complexity of extending to vectors and matrices that happens all under the hood. All right, here's some pseudocode that summarizes that, just to emphasize the importance one last time that we have to evaluate everything in a forward pass to get those intermediate values of h, y hat, things like that. And then we save the h's and y hats and z's. Those aren't anything about what we were interested in solving for in the first place. We need to save them to then evaluate these local derivatives and pass those on backwards as we go. But that's the summary. Is this all happens when you hit enter. So you don't have to think about it, but you should, especially if you encounter issues and you can think of things you've learned in this lecture which might indicate why or why not your issues are arising. And then at the same time, yeah, it's really important to consider the complexity of these operations and how those are limiting what is possible currently in TensorFlow, right? It takes a long time to develop these newer features, specifically because of all of this graph and derivative passing infrastructure that needs to be baked in, right? To make it as easy as pressing enter, you need to be a little bit sympathetic with those complications that all of the probably 500 engineers at Google and or Facebook are facing as they make this for free for all of us. So.